This media was gratuitously produced by Clear Contributions Audio and Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
All right then, if you're ready, I wanted to get going on chapter 7 today. So this is still where you have pi bonds. It's still where you're going to develop an electron deficiency of some type or another. But now, as I said before, electron deficiency is the issue. And so all we're doing all semester is I'm showing you what resources do you have for sharing some electrons with that radical or carbocation to stabilize it until you can complete the reaction. And so we just looked at resources that are on adjacent atoms, so you're overlapping bonds with adjacent atoms or non-bonded electron pairs, or because the adjacent atoms are sharing bonds, you might be able to shift something over. But those are all electron resources that are right there. So this next chapter is, okay, now we're going to go a little farther out. What electron resources do you have from 2 atoms away? And I'm going to be shifting back and forth between the textbook and the workbook, but you guys can just stay on the workbook. I'm just going over to the textbook to pull up some graphics. Anyway, the key idea here is if an atom that's 2 away has non-bonded electron pairs, it can reach over, across, and span the distance and share electrons for a minute until something better comes along. But it's a little bit of a stretch, so you don't want to leave it like that. And you're going to form a strained ring. To introduce this topic, I want to tell you the story of the little Dutch boy. You know I'm half Dutch. Van Kyken is Dutch. And I have found through the years that when I said, it's just like the little Dutch boy, that I have students who look at me like, I don't know what you're talking about. And that just makes me cry, because that your education is so woefully inadequate that you don't know the story of the little Dutch boy. So I have to tell you the story. And kind of to introduce it, I've been to the Netherlands several times to see where the Van Kykens came from, and there are still Van Kykens there. I visited the towns that they came from before they came to America. And they live right on the North Sea, right, like you can walk across the street practically, and you're at the North Sea. Most of the Netherlands, about 50% of the Netherlands, is actually below sea level. What they did was they would build walls and then they would pump out the water to kind of expand the country. And so once you're up by the North Sea, I mean, they've done that, and you go up on top of the wall at the sea, and you look out, and here's sea level here, and you look down, and there's the village down below. I mean, they're way below sea level. And so the walls, they're called dikes. Those are there to hold back the ocean. And if there's anything that happens that the integrity fails, then you get this wall of water coming, and lots of people die. I mean, it's been catastrophic over the years sometimes how many people die when the wall gives way. And so the story of the little Dutch boy kind of addresses that. The story is that one day the little Dutch boy was walking along on his way home, and he noticed that there was a little hole in the dike, and there was a little bit of water coming through. And he knew that if that water kept coming through, it was going to force the hole bigger and bigger and everything until the dike failed, and everybody in the town would die. So in an act of quick thinking, he stuck his finger in the hole of the dike, and he waited for somebody to come. So it's not an ideal situation, right, to stand there with your finger in the hole of the dike. So you want something that's a more permanent fix for that problem. But in the process of him keeping the water from coming through, then that meant that it didn't get any worse, and so the whole town was saved. And so anyway, a little bit later, somebody came along who saw him and came and repaired the hole and everything, and he was a hero for the town. And he stood there, even though it was raining and cold and everything, but he stood there with his finger in the hollow dike, but waiting for something better. And it's the same kind of situation here, so don't draw this out, because this is kind of dissected into steps when really it all happens at once. But it's kind of like you have the double bond, and you have something that's going to add on that has fingers or electron pair. And so when this bond opens up to start to form a new bond to this atom, and you start to develop a carbocation here, it's like a hole in the dike. It's like this crisis. Wah! And so this atom says, wait, I can plug the hole in the dike with my 2 fingers. I don't know, somehow this is a 2-finger issue. Anyway, I can plug the hole here, but I don't want to stay here like this, because then that means that you've got this strained ring. So you got this little boy with his arm ready to fall off from the strain of, having to hold it like this. His arms are cramping. So you're waiting for somebody to come along and fix the issue. And so you've got something with a non-bonded electron pair here that can come and say, okay, I got this as a permanent fix. You can let go now. And so it goes like that. And that's the big thing from this chapter. Anytime you have something adding on that has a non-bonded electron pair, it can share that to take care of the situation. Because a strained ring is not good, but better than a carbocation, that's what happens. And so that's why it's second on your list of priorities. But you don't want to leave it that way. The strained ring is very reactive. That's second on your list. So it is so highly reactive, it will react with whatever has a non-bonded electron pair that runs into it. And so you're looking for the highest concentration, just like before. So it's like you can kind of think of this like it's a carbocation, except for you can't shift anything because you've got a bond there temporarily. Okay? Otherwise, it's the same kind of principles. So that's what we're doing today. And I will show you a graphic for it from the textbook. So it's kind of like it's starting to react with it. The electron cloud deforms because it notices that you're starting to develop a carbocation there. So it starts to kind of like deform over, and it forms that strained ring.
So this would have been happening whenever we're doing our previous reactions. This would have been true. So
It would have been true, except for hydrogen doesn't have a non-bonded electron pair. So all I can do is stand there in horror watching the hole in the dike getting worse and worse and worse.
it's like the little boy that didn't have any fingers.
Yeah, that's kind of sad. But it's true. So now that you got that, you've got about half of the chapter. This is all we're doing in this chapter. So I just need to get you to be able to apply it. So there's going to be another strategy that I'll show you another day, and that involves boron the moron. And boron the moron, you know how it can have 3 bonds, or 4, or 3 would be good, but 4 is fine, but I'd like 3, but no, I'd really like 4. Anyway, how it goes back and forth. If you have boron with 3 bonds, it wants to accept the pi bond, and then it throws off one of the bonds because now it has 4. So that'll be a second thing that we'll be doing. But for today, sharing non-bonded electrons from an atom that adds to the pi bond. Because anytime an atom adds to the pi bond, it's automatically 2 atoms away from the developing carbocation.
Is there a paper copy?
No, and I don't have my computer. It's in the IT repair shop right now, but that has the paper copy. So I will try and get one for you tomorrow. Okay? How many of you want a paper copy, by the way? 1, 2, 3, 4. Okay, I will make you copies. So I said you're about a third of the way through the chapter. We got, most of it is the non-bonded electrons that you're sharing. They just told you about. Boron will be another reaction, then we got to go over stereochemistry. And please let me know if the writing is ever too small for you to see it or something. I guess as we're going along, I'm finding out where I want some more answer blanks. Okay, and the way that, and so know when and how to share a non-bonded electron pair with a developing carbocation. You do that if the atom that's adding the pi bond has a non-bonded electron pair.
So when you, just for terminology's sake, when you say the element adds the pi bond, would that have been the A?
Yeah. Well, I had two A's up here, but the first A that added on, yeah, here. Yeah. So I guess more effectively, you could say if the electrophile that reacts with the pi bond has a non-bonded electron pair.
First A is kind of like the temporary savior.
Yeah, it's the little boy.
Yeah.
And the second A is like the grown man who comes along with the spackle and everything or whatever, yep. To do a final fix. Good. All right, so the general mechanism, this happens in the same step. So that's why I said don't write it the way that I'm doing it right now with the carbocation, because you never have a carbocation there. It all happens at the same time, but I wanted to kind of show you it's like you're breaking the bond, you're starting out with a carbocation, so you share. It actually happens in one step. You can figure out how to do the arrows based on which carbon would be more likely to be the carbocation if you didn't have that additional resource. And so the electrons go to the developing carbocation, in this case the tertiary. So you're drawing the arrows as though the pi bond's going to react with this atom, and then that's going to share its electrons so that you get that strained ring. In addition, if this atom is forming two new bonds and it was happy before with just one, then if it's forming two new bonds, then 3 bonds is crazy talk. So you got to let go of something. So it will let go of the other, of something that's attached to it. So now I have something that I would really love your feedback on, and you don't have to give it to me today because you're going to have to work with this for a while and see what works for you. But you know how all along we've been drawing molecules like this with stuff coming left and right and up and down and stuff like that. Since this is trigonoplanar, the actual molecule doesn't look like this. It looks more like that. See, so what I'm doing is I'm moving these bonds down here. I'm just kind of squishing it this way, and I'm squishing this way. And one advantage of redrawing it like that is you can better see the stereochemistry as you're working problems. And the big thing here is that if I'm telling you that you're going to react with this carbon, let's say, when you have a strained ring here, you're going to probably say, oh, there's no room for it. Look, you got something there already. But if you draw it like this, then you might be able to see better that, oh, okay, I've got room to do that. So in the textbook, I've got it drawn so it matches the actual stereochemistry to help you picture. And I was considering, you know how I was fussing in the last chapter and saying, I'm not sure what your thoughts are going to be. And I had asked you whether you wanted to have me draw things with the actual stereochemistry or draw it the easier format like this. And we were kind of iffy about it, but be thinking about that question as we're going through this chapter too. This is going to be better, I think, in the long run for stereochemistry, but it's hard to get you to go from this to this sometimes, and so I wasn't sure if you were going to make that leap or not. So be thinking about whether it's better for you to just draw it out and worry about stereochemistry later, or if it's better for you to draw it well with the stereochemistry pictured. But I kind of did it with the stereochemistry here, kind of thing to help you picture. Okay, as I said, you're not going to leave it like this because the poor boy is standing in the rain with his arm cramping up. So you want to react it, and you notice that if it's drawn with a stereochemistry like this, that you have to react from the opposite side because that strained ring is blocking one whole side of the molecule. So you have to react it from the opposite side, and you're going to react it with the tertiary carbon because that one is the one that has the weaker bond because it would be the better developing carbocation. So you're going to react it with that. Okay? All right. So the reason why an alkyl shift or hydride shift can't occur. Yeah, sort of. So you have to have an unoccupied p orbital, and it's occupied because you have that extra bond. So in the last chapter, I had an answer blank where I said, what are some examples of things that would never allow a shift? And we wrote down a radical, because you don't have an empty p orbital. This would be the second case for this semester. Okay, and I'm not entirely sure why I put 4 answer blanks for the most common examples of atoms that share non-bond electron pairs. I think I could summarize it into 2, but that's okay. We'll go with this. And technically, it could be any atom that has non-bonded electrons. This is just the ones that you're going to tend to see in an organic chemistry class, okay? But any of the halogens, chlorine, bromine, or iodine, and that's why I'm saying I could have reduced this down to 2 and just said halogens. Or mercury is going to be another common one that you see. Mercury is a large atom, of course, and it has a ton of valence electrons and d orbital electrons and such that you could use to share with something. So this is another case where it's really good to draw in the non-bonded electrons as dots before you venture off into something. think I'll draw on the iPad because it's the marker is not really that dark that you can see it. But one thing that you're going to run into that you're going to see is I'm going to say, okay, we're going to react bromine Br2 with a pi bond, and you're going to list and label everything. And so you're going to say, okay, where's the electron deficient there? You don't have a difference in electronegativity. So you know how normally you wouldn't write a partial positive and partial negative with this. But the deal is, if you get that close to a pi bond, that these electrons in the pi bond are going to cause these electrons in the bromine to kind of squish over. Remember London dispersion forces from general chemistry, the squishiness of the electron cloud, and that's caused because you're getting electron shells too close to each other, and so they kind of start to like try and get away from each other within the electron cloud, and so you deform the electron cloud. And so you're going to induce a temporary partial positive here just because the electrons are getting away from the pi bond. And so you're going to write in a partial positive and partial negative for halogens, even though there isn't a permanent positive and negative there, just because of London dispersion forces. Okay, so that's the reason why partial positive and partial negative charges can be assigned to atoms in a molecule such as chlorine or bromine. The pi bond electrons repel the electron cloud, and that creates a partial positive. So I'm sorry about that one. That one's a little bit enough to make you bitter. Just try and remember that one. Especially with large halogens like bromine, then you have a large electron cloud, and that's easier to get it to deform. Remember from Gen Chem with London dispersion forces, we talked about the big marshmallows for s'mores versus the little rock pebbles in your hot chocolate, the marshmallows. Yeah, the bigger the cloud is, the squishier it is, and so something like bromine has a fairly deformable electron cloud. Are we good to go? All right, so now all that's left is for me to show you how it applies to particular problems. And, shoot, I don't want to have you cheat here and tell me. So for each of the following reactants, it says, draw the mechanism for the formation of the intermediate, and that's fine, but first, I think, select which can form a cyclic ion intermediate. So going down your list, what I'd like you to do is, if you're thinking about reacting a pi bond, first identify what would be the electron deficient atom it would react with in each case, and then decide if that atom has the capability to form a cyclic ring. And just to warn you, there's one on here that can't react at all. So if you're going, I'm bitter, where does this react? Then that's fine. There's one on there that doesn't.
What's the cyclic ion intermediate?
That's the, that. And it's called a cyclic ion intermediate because usually the atom that adds on goes from having one bond to two, so it's going to have a positive formal charge. That was a little feature that I didn't have on that graphic, unfortunately. And you can draw out, for your homework tonight, you can draw out what the ion intermediate is, But for right now, which ones would have that cyclic intermediate and which ones would just have a carbocation? Since we're kind of short on time.
B would be the
Good. B would be a cyclic ion. Mm-hmm.
what A?
Now, because the electron deficient atom that you're adding on there is hydrogen. And hydrogen doesn't have the non-bonded pair, so that's why you're stuck with a carbocation. See how that works? Uh-huh.
For C, it does have the unbonded electron pairs, but it's negated.
Uh-huh.
So
So there you have a pi bond that's electron rich. And what about the hydrogen? Is that electron deficient or electron rich? And so you don't have a reaction. Remember I said there's one of them that you're going to be like, okay, what am I doing with this? That's exactly right. Okay. And see how I have if a reaction cannot occur, right? No reaction. I'm trying to get you to not be mindless about this, but to actually look for electron deficient. I think that's true.
So, in terms of the steps when you start choosing, do we first look, like in B, what helped me, I'm like, okay, it's halogen or mercury. Is that the right approach?
Yeah, so you're looking for what is electron deficient. So with the chlorine, you have the artificial partial positive and negative, the temporary. And so the chlorine adds on with an electron pair, and so that's where you're going to get the cyclic ion. So just make sure you're on track for your homework where you're writing out the steps. A, you're adding on hydrogen. You can't do anything about anything. Maybe a shift, but you can't share electron pairs. With B, with chlorine, yes, you can, because chlorine has non-bonded electron pairs. C isn't going to react. D, hydrogen is going to be the thing that is electron deficient, so you wouldn't have any options to form a cyclic ring. There you're thinking instead of maybe shifting. But E, mercury, you do. Okay, so follow the pattern that I had shown you here when you have the cyclic intermediate where you react it and you let go of one of its bonds to something to form the intermediate, and that'll be your homework for tonight. Okay? Your homework is actually write out the steps, the mechanism and the steps and what the intermediate is, like here with A, where you're writing out what you got going on there.